Alright, a farmer is using a AC motor to power an irrigation pump. The motor needs 900 volts of RMS AC to operate correctly. When the motor is running, the motor draws 50 amps AC current. Calculate the power input to the motor when the pump is operating correctly. Right, now this is a relatively simple calculation. Power equals VI. The V we use whenever we're dealing with, and the I as well, whenever we're dealing with AC is the RMS values. These are already given to us in RMS. It's already in RMS, it's already in RMS. So we don't have to be timesing or dividing by root 2 like we did in question 3. It's all ready to go. That was a common mistake in this question when it was set as an exam question. So this is just 900 volts times 50 amps, which gives 45,000 watts. And they want their answer in kilowatts. So to go from watts to kilowatts, we divide by 1,000. So divide that by 1,000, we get 45 kilowatts. 45. Right. Number B. Supply electricity to the AC motor that drives the pump. There's an AC generator installed at a waterfall some distance away from the pump. The generator provides current at a voltage of 1,000 volts RMS AC. There's two aluminium wires generating to link here to here. Here's the wires here, and they have a total resistance of 7 ohms. And the motor that we're running has a resistance of 18 ohms. Calculate the current flowing through the aluminium connecting wires. Okay, one way to think of this is our AC 1,000 volts. This is a circuit diagram. Each of the wires we've got kind of looks like resistors, like this, and here is our, we'll call this our motor. Right. Yeah, our motor. The wires have a total resistance of 7 ohms. So between them they have 7 ohms, so they have 3.5 ohms each. We don't really need to use 3.5, it just is to show everything's set up. Ohms, and this is 18 ohms. Okay, calculate the current flowing in the aluminium connecting wire. So we have the total voltage. We also have the total resistance, because these have 7 between them and 18, so 18 plus 7. So this is a series circuit. We can just add the resistances together, 25 ohms. So how do we, when you want to find I, current, what's the relationship between I, V and R? I know V equals IR, so if I rearrange that by dividing both sides by R, I get I equals V over R. And I want to work out the total, so these have to be total as well. Voltage total, we know, is 1,000. That's the total voltage from this guy, yeah. And the total resistance, not 18 and not 7, the total resistance is 25. And 1,000 divided by 25 gives me 40 amps. 40 amps. Alright, let me just open up the other file. C and D. Alright. Determine in this case whether the pump will operate correctly. Support your conclusions with calculations. There's a number of ways of doing this. Is it getting the right voltage? Is it getting the right current? Or is it getting the right power? The way that I've chosen to do it, one of the ways is to see, is it getting the right power? So in question 1, it showed that it needs 45 kilowatts to operate correctly. Sorry, not question 1, question 4A. Operate correctly. This is what we calculated. So let's calculate how much power it's actually getting. So again, we've got a number of power formulas we can use. Power equals voltage times current, or we've got power equals I squared times R, or we've got power equals V squared over R. Which one are we going to use? We could, well, some students opted to use this, and they opted to use VI with the 1000 volts they got from question part B, and then times it by the 40 amps they calculated. This isn't correct, okay? The AC supply is giving 1000, but we don't know what voltage is being used by the pump at the moment. We don't know that, so we can't use that one. We do know that 40 amps, because it's a series circuit, 40 amps flows through the wires and 40 amps flows through the pump as well. So we do know this, we know I, and from the last question we know R as well. So we can use this formula. So if we use this one, I squared R, we get P equals I squared R equals, we just calculated 40 squared times the 18 of the pump, because we're just looking at the pump. 40 squared times 18 is 28,800 watts. And that is not our 45,000. So it doesn't operate correctly. Right, and the last one in this, part D. The farmer wishes to reduce the power loss in the electrical connections between the AC generator and the AC motor powering the irrigation pump. It's not possible to move the position of either the generator or the motor. Identify and describe two different changes that reduce the power loss between the generator and the AC motor. Alright. Power loss, this is really saying what is the power loss in the power lines. And hopefully in your notes somewhere you can find that the power loss in power lines, P loss, the power loss, is equal to the I squared times R. Okay, the current going through the lines times the resistance of the lines. So if we want to make this smaller, we could either make I smaller or we could make R smaller. So those are our two different changes we're going to be talking about. So the first change is, let's write this in our answer, P loss equals I squared R. So decreasing R, and there's a couple of ways we can decrease R of lines by, we could make lines thicker by making lines, the power lines thicker, or another way is to use a better conducting material, for the lines. Both of those things will decrease R, and so will decrease the power loss. The other one is again P loss equals I squared R. So decreasing I in lines will also decrease the power loss. How do we decrease the I in the lines? We could use transformers. So install step up transformer by generator and a step down transformer by pump. This will increase the voltage in lines and decrease the current. And we've already set up at the top, decreasing the I in the lines will decrease the power loss. So we've got our argument there. Decrease the current in the lines. Done.